Thanks. Yeah, so we have this nice fancy title, and by the time we wrote that paper, I thought it is nice to have fancy titles, but then I think at the beginning of this year, there was like a journalist who read a paper that had an attack, a side channel attack on Kyber, and immediately threw out this headline of, oh, the upcoming standard is broken, yeah? And I got these emails like, do you know this attack? Do you know this attack? And yeah, okay. So this is a joint work with Hauke, Steffen, who by that time was our master student, brilliant master student, Lucie, Kogelheide, and Tim Güneysu. And a bit of the, oh, I'm glad my corrected version made it this morning. So I've had spings. I missed the H. So yeah, so a bit of the motivation, back then there was not yet this NIST selection when we started working on this actually. But we could have guessed that the same argumentation I'm about to make would hold similarly. So we have this, now we have this selection of Dilithium, Falcon, and Sphinx. And if we watch, are there embedded use cases for each of these schemes? And then probably Dilithium is like the prime choice. And yeah, you could argue that Falcon should be in brackets as well. We have had it yesterday. Like it's kind of an open question how to implement it constant time. And that's even, yeah, that's the least problem Falcon has. And for Sphinx Plus, I actually, yesterday I've learned that it has this nice property of low RAM, of low stack at the signature limbo, yeah. Still it's painfully slow, and I think we'll have to wait there for hardware acceleration for Ketchak or something. Yeah? And then looking any further, what about masking? What about side channel attacks? Can we make it secure against side channel attacks? Then the answer is yes for Dilithium, although it is quite complicated. And the answer is no for Falcon, just because we don't have a clue how to mask floating points. It would be possible probably in some Boolean setting, but it would be painfully slow and inefficient, infeasible actually. And I'm not aware of any works towards masking Sphinx. Then again, it's also some kind of slow already, so it would be even slower than in embedded use cases. And then if we zoom into this Dilithium, by that time I could already count a lot of papers on like software side channel security of Dilithium, and now, okay, that's back then, yeah, so I'm very happy to see first papers that look into hardware-specific aspects of side channel attacks on Dilithium. Yeah? So yeah, right now there's at least one, at least ours, and the one of Marco. Yeah? So what we did is we did a first side channel analysis of Dilithium hardware implementation. By that time, it was the most advanced one by Luke, actually, who had the first talk in the session. We do so with a special emphasis on practicality. We just use standard techniques for this, I have to admit. Yeah, so that's long-known techniques: simple power analysis and correlation power analysis. We introduced some tweaks to make them more efficient. So that's another slide contribution there. And then we also explore efficient countermeasures. And what do I mean by that we emphasize practicality? So we just used a standard RTX 7 discovery board, FPGA discovery board. We clocked it at 100 megahertz. And that's the first thing. So many academic works in the side channel community tend to, and it's completely valid to do this, to have a very low clock frequency, for example, like 4 megahertz, because then you find more leakage. Yeah? And for leakage assessment, that's a totally valid way. Yeah? Still, yeah, we opted for high frequency, and then we also had our FPGA package and the whole discovery board unaltered. So we did not integrate any measurement resistor, we did not open the FPGA package. Instead, we put a near-field probe next to a capacitor that is in the power path, and then we know that the electromagnetic emanation is somewhat proportional to the power consumption of the whole FPGA. So that means although we do we use a near-field probe, we did not probe specific modules of the implementation, but the whole power consumption of the whole FPGA, which is also, I think, or I would say, a bit more a realistic scenario. Then a short recap on Dilithium keys. So that's highly simplified, I know. So we have T equals, or T is computed to be A times S1 plus S2, where this is a matrix of polynomials, and these are vectors of polynomials. And then A is uniformly random from ZQ, and the secret key is uniformly random from the set minus eta to plus eta. Yeah, and if you have a look on this, so it's encoded to be so such that each coefficient is positive. And if you then have a look at the Hamming rate of the coefficients, so of the decoded coefficients, in the secret key you can see that the Hamming weight is highly diverse. So at least, the least we would expect that we can do is that we can distinguish between the non-negative and the negative coefficients, so to determine the sign, or even, so you can see -1 has Hamming weight 10 and -2 has Hamming weight 22, so that's also quite a big difference, yeah? And yeah, I bet you know the answer, can we classify them? Yeah, we do have even more there. So that's only the decoding step. Right after the decoding step, there's the entity, and in that specific implementation, they have a 2x2 butterfly construction, but anyways, in any implementation, there will be some kind of a butterfly construction. And that does process four coefficients in parallel. And so you can see the coefficients B1, A2, and B2 are multiplied by the triple factors, and A1 is the only one that's not. And this multiplication then yields an even more diverse power signature. So we expect that when we include this first entity stage into our attack, that it's even, it yields even better results. Maybe a word on, because you might not be too familiar with these techniques, I just thought I'd briefly introduce them. So profiled SPA is a very strong attacker model, I have to say. That means in a first stage, the attacker has access to a profiling device and he has full access over it. So he can also measure the power consumption for different secret key combinations, and he can program it with arbitrary secret keys. And in the second stage then, the attacker has access to a target device and then aims at obtaining the secret key given his prior knowledge. And those are the results, and as you can see, that's more or less as we expected. So A1 is, you can see the confusion map is slightly worse than the others. For this attack, we used 50,000 profiling traces, which is not a lot, I think. So what you can see here is the probability of classifying each coefficient correctly with a single trace attack. So we use only a single trace, and then what we also can do is we can combine the classification of multiple traces, and then for recovering A1, we can use at most 35 traces, and then we have it in 100% of the cases. And all other coefficients need at most 4 attack traces to classify correctly. The second attack that we tried that we applied is correlation power analysis. This is a weaker attacker model, so the attacker does not have at any point access to a profiling device where he can program arbitrary secret keys. So the attack in the end is somewhat stronger, and there the target is during signing the multiplication of the challenge, which is part of the signature candidate, and the secret key. And we chose so we didn't just choose it, we just tried out several other power oracles, for example, Hamming weight and Hamming distance, and interestingly, they yielded worse results than the single bit power oracle that we used. And then in the paper, we have several other results for example, we explain a method that halves the number of hypotheses that have to be processed during computing the best hypothesis, and also the impact of noise generation, for example. So whether noise generation would be a good countermeasure, and I can say it increases like the number of traces by 1 order of magnitude, but it's no like complete countermeasure, obviously. So now some countermeasures. Just so these simple power analysis can often be countered effectively by shuffling. We did actually not try this out. So because in the end, what you often want to do is just masking, because it also offers protection against the correlation power analysis. And then I'm happy I didn't make more background, because Marco already covered this. So the problem is already storing the key. Yeah, that's a big issue. And you can do. And generally, we have two options for masking. We can do Boolean masking, and we can do arithmetic masking. So the pro for Boolean masking is that when you compare the size of the key that you have to store to an unmasked implementation, that grows by a factor of d. But the problem is, with this Boolean sharing, you can't do arithmetic operations efficiently. Yeah? There is an asterisk, I'll cover that later. And on the other hand side, there's arithmetic masking. We can do polynomial multiplications easily, and you can do entity shareWise and all this stuff. But the problem is that we have this bounded secret key. Yeah? So it's just bounded from minus eta to plus eta. It's 3 or 4 bits. And for an arithmetic masking, then we would have coefficients in ZQ, so 23 bits times D, which is a huge overhead factor. So ideally what we want is we want a Boolean masking stored, and then an arithmetic masking during processing. Yeah? So about the multiplication, actually I have to say, so you can, it's totally valid to do the multiplication in the Boolean domain completely. So it's C is sparse and just small and sparse, and S is also small only. So you can do an efficient schoolbook multiplication there that is totally possible with Boolean masking, but it is slower than using entity and would require additional randomness. For example, if you use Pineye gadgets on this direction. Still, it's a valid point to look at, I think. So one thing that the last thing I want to cover in this talk is what we propose you could do is a masking conversion with integrated decoding. And there we start with a Boolean shared encoded input. So Boolean sharing I indicate by red. And then we construct this weird looking value, which is more or less a sharing, a Boolean and mixed Boolean arithmetic sharing of this value 2 to the 23 minus q, which is the modulus minus eta. And then we do a modular addition. So this weird value 2 to the 23 minus q enables an efficient modular addition over Boolean shares, and minus eta we will use for the decoding step then. And afterwards, after we have done this secure addition over Boolean shares, we actually can just unmask this value. So why can we do this? What we effectively did is we added a random value to our encoded and shared Boolean shared secret key coefficient. So at this point, we have effectively 3 shares. So we can just combine 2 of them. Then for correctness reason, we have to negate this. And combined with this x, we have an arithmetically shared decoded output. And that's the idea. And yeah, what's the cost of this? Yeah, so there we need a secure 3 plus 23-bit adder. And this other thing is just a secure conditional addition of q. And both of them can be done very efficiently with parallel prefix adders. There's also research on this, how you can do this over Boolean shares and how costly this is. And compared to the whole implementation, it's really not a big deal. So finally, what did we do? We did like the first side channel analysis of Dilithium in a hardware implementation. We did so with standard techniques, and we also explored efficient countermeasures. Why is that important? Obviously, Dilithium will be standardized soon, and it's not good to have this little knowledge about like hardware-specific side channel analysis. And yeah, future directions that I'd like to see would be a fully protected hardware implementation. I think we're getting there, and hopefully at some point soon there will be one. And also what I'm looking into is a potential benefit of using only this Boolean masking approach for some other reasons as well. And then one thing that's also fairly unexplored is fault attacks and countermeasures in hardware. So if you have any questions, I'm happy to answer them now. There's also this nice link to the ePrint, and if you scan the QR code to the right, there's also the other authors' emails in it. Thanks for listening. Oh, I was a bit quicker, yeah?
I read your paper. I noticed that you used t-test for evaluating the countermeasures. And I assume that was the first order t-test.
Yes.
How would the countermeasures you propose affect feasibility of single trace attacks, which don't limit themselves to only information in first order moments, statistical moments, like
I understand. I think it's been quite a while since we did this. I think we still rely on the t-test, and I know that's not a complete argument for security there. You're right. I actually don't have an answer to that. So you're right. There might be some way to still attack this. Yeah. But then again, I would encourage research in this direction. Yeah. So that's a big gap, I think. Like side channel analysis and countermeasures for hardware implementations.
No other question? Then I think we can thank the speaker again.